we go.
Yeah.
Okay, so first of all, I just want to say thank you, Manuel, for taking the time to be interviewed by Space Talk. I'm absolutely thrilled that Neutron Star Systems is focusing on developing an electrical propulsion system for in-space propulsion. And it's very fascinating because missions such as bringing cargo from Leo to the moon, or bringing cargo to Mars, were once considered a sci-fi concept. But now they're becoming a reality due to this, and this is something that you're tackling. So it's quite exciting to hear all about that.
It is, yeah, it is indeed exciting. And how would you like to proceed now? Should we follow your questions for the? Okay, good. Okay, let's talk about first. Let's talk about the inspiration point. So
Perfect.
one of the things that really inspired me, it was not the things, but the persons. You see, this is something that is coming mostly from the inspiration of persons that trusted me. One of them is my friend and main research partner, Professor Georg Hedrich, who I came to meet 3 years in March 2017, more than 3 years ago. And we lay out the fundamentals of what is it called, the Supreme Thruster, and then later on Neutron Star Systems. So it inspired me the way he understood, or he understands, the problem of propulsion in space. And it helped me also to understand what is the really mass of quality when making space missions, and it's a payload mass fraction, you see, and how power, propulsion, and payload mass fraction will play a fundamental role on articulating a space infrastructure. You see, we don't do it now because it's just too expensive, you see, and you need the type of infrastructure we need to build. Requires transportation capacities and payload capacities. So he helped me to understand that, and he showed me, helped me to understand the technology. And when I understood the technology, I knew, I have to do this. I have to build this thruster and put it into the market. So that was one thing, my mother, and also I was a Boy Scout. It sounds old-fashioned, but I was 8 years Boy Scout, and I did a lot of camping outdoors. And you see, in Venezuela is equator. You see, so you can see the totality of stars. So you see much more stars than what you see here, for example, in Europe. And I found that that's really fascinating. So I came to space through sneaky ways, because I learned materials, I learned superconductors, I learned electric propulsion electric propulsion, and then ergo, you see, I have to do it in space. And that is how I came to the space sector. And Neutron Star Systems came as a result of two proposals, research proposals for European funding. One is called Supreme, and another is called MISS. And both proposals were for programs such as Fed Open and the Space Call, for 2 million euros the one and 3.5 million euros the other one. And Supreme did not get funded. It was about
So sorry there, Manuel. Can you hear me?
I can hear you.
Oh, perfect. Sorry, it looks like we had lost connection there temporarily. Do apologize for that.
Okay, so well, basically we put these two proposals, and one of them was awarded for funding from the European Union, and for us was the real indication that the time was now. to to found the company and start the commercialization, because the research times in space are long, etc. And we were right with this approach, because lately in September, New Zealand decided to put 6.5 million euros on the development of superconductor-based electric propulsion technology with AFMPD. So, which is an indication that they have planned a fly mission for 2025.
Yeah.
So, one way or another, in 2025, the market for high power electric propulsion will be open, you see. And
that is so exciting.
And we will have the possibility then to plan new missions. So this is the reason why Neutron Star Systems was born. So if you help me with the next question, I go to it. I have the email here.
And I believe
So what are the challenges you encounter? Where?
yeah. Please take us through those challenges and how that led to one of your newest development, like you mentioned previously, the Supreme Thruster, and what makes that so unique as well.
Well, I think the major challenge was to take the decision to make it, Celine, because at the end of the day, as a non-space entrepreneur, entering into the space business, it was a very difficult decision. You see, it's a very conservative market. It's very difficult to enter. You see, the demands are very high. But that was one of the major challenges. Also, the lack of how would I say, the people in the space industry didn't understand the value of superconductors. You see, let's put it this way. I'll show you. This what you see here is a superconductor tape. It's able to carry 800 amps per square millimeters, which means you can build very power dense appliances, very power dense and lightweight equipment. You see, that can be used for power transmission, for power generation, for electromagnetic field generation, for power. That at levels of powers that were not dreaming space, and now you can do that. You see.
So sorry, Manuel, I cannot hear you anymore. Can you hear me?
Yeah, I hear you.
Yeah, sorry. I'm not sure if it's
let me do something. I'm going to use, because I think that in the night here in Germany, every second household is on Netflix or watching stream television. And that makes it quite complicated. So let me just change this. So while I do this, as I was saying, the major challenge was to bring the idea of to bring the solution of power upscaling in space to space people, because they are not used to it. You see, they are used to conventional technology, long engineering programs with, qualification of all the components, etc., etc. And this is totally new, because it doesn't only have the superconductor, but also have the cryogenic system. You see, and you have two systems integrated in one, and they have to function. You see, so that's a really big hurdle to pass. You see, but despite all this resistance to embrace this technology, let's call it like this, is the only possible feasible way and efficient way to do it economically. you see, because when you do big missions, when you do high power missions, you will need power. You will need power distribution, and with conventional technologies, you will have too many losses. The power at the check-in will not equals the power at the check-outs. Ergo, the system efficiency of the whole mission will suffer. And we understood that, and some other people understood this, and that's why we're doing this. So the uniqueness of it is basically based on the electric propulsion system. And to be more specific, MPD thrusters have something that no other propulsion system have, which is what is called the propellant flexibility. They can be operated on almost every sort of propellant, including propellants such as argon or ammonia, which are 2 orders of magnitude cheaper than the status quo, xenon. So that advantage is not only relevant for the case of using low-cost propellants, such as argon, you see, but it's also relevant. Are you there?
There it goes. Yeah.
Okay. So since you can operate a chemical electric, means you can operate also the thrusters on mixtures of hydrogen, oxygen, and for example, ammonia. And you can have a spacecraft that can maneuver at high thrust and also a high specific impulse, which is one of the major characteristics of the thruster. So you have hybrid architectures, propellant flexibility. You have also the research heritage. It has been researched over in 6 countries so far. China is one of the largest countries joining, and New Zealand now in September. So now we have 7 nations aiming for the development of this technology. And the heritage at research level is amazing, you see, because it's one of the most researched technologies existing. It didn't fly before for the simplicity of, well, not the simplicity, but one of the reasons is because of the electromagnets were made with copper as conventional technology. And they were too power hungry, too inefficient, too heavy, not flyable, you see. Among those was the erosion of the materials and the sputtering of the materials and you see the wearing of the materials due to the high powers. And the fact that at that time there were not the technologies for coatings to make materials resistant to this kind of erosion. So 30 years later, with superconductors fully available and commercial from the shelf in form of tapes, as I showed to you, you can basically make these electromagnets with superconductors and integrate them in a very, what is it called, a very robust and simple architecture. You see, less complex than, for example, a Hall effect thrusters or the Vasemir rocket, which is a hybrid of radio frequency, antenna, helicon, and MPD. So for the case of high power, you see, you need something that is reliable, that is robust, that is simple, and the most important attribute is the scalability. You see, you can scale from 750 watts to 1 kilowatt, 1 megawatt. You see, 1,000 kilowatt. And that flexibility gives you the possibility to solve the problem of propulsion by the clustering of different power classes. And you can choose between 50, 30, 20, you see, you have a wider flexibility, less complex systems, you see, and you have the problem of the power heat losses partially resolved by the use of superconductors. If you work in a fully superconductor system, this problem can be minimized to a very, very low value, which means it gives you a very efficient system. And this is important because this is going to be fundamental to reduce the travel time, and B, also secure that you have the most efficient mission, either because you maximize the utilization of the propellant to go at the lowest ISP, and let's say reduce the amount of propellant you need, maximizing the capacity of your cargo, or because you want to go faster, and then you use more propellant and you increase your ISP, you see, and then you can basically go faster to areas like the Van Allen belt, for example, if you want to reduce cosmic radiation or something like that. So, and that is the uniqueness is based on the fact that with such compelling proposition, you can generate millions of savings for existing mission studies and reference missions for cargo and moon. So, there is a strong economical argument speaking for the use of the technology and its development.
Yeah, and like you've said, like with upcoming, high power space missions, you will require spacecraft which are larger and heavier and need to travel further and faster. And that's where you come in, and you assist with that sort of transition to be able to do those sort of,
So the idea, because the idea is you need to understand that, by bringing just small pieces of cargo to moon, we're not gonna build the base that we would like to have and build, and we are able actually to build with the technologies we have available. What we need is cargo transportation capabilities.
Exactly.
But that has to be done at that affordable price.
No, I couldn't agree more.
Current propulsion technologies like Hall effect thrusters do not solve that problem. Yes, they have the flight heritage. Yes, they have been since the 70s around, and they're reliable and all of that. But cargo is another league. You see, that's the league of mining. That's the league of power generation. That's the lead of the stuff that you really need to build something that is significant in the moon. Okay, we can be little matches, houses, or you need to really think, because this is a question of economies of scale.
Exactly.
And that's also one of the problems that we address, you see.
That's very, very exciting. And Manuel, that brings me, I guess, to my next question. This is quite exciting because, now we're looking at going back to the moon and making it a more permanent residency there. And of course, continue our journey to Mars. Can you tell us why, electrical propulsion is the solution for these long duration missions, and how using, high temperature superconductors has been a game changer? Because it obviously has changed the way that we're going to be able to continue to travel in space.
Yeah, well, let's start for electric propulsion versus chemical propulsion. You always need chemical propulsion in order to, overcome gravity, Earth's gravity. The problem with chemical propulsion is that they have a very low specific impulse. You see, they have a very high thrust, but low specific impulse means the conversion from mass to kinetic energy is very, the rate is very inefficient. You need, for example, from 100 tons total payload, 2/3 are propellant.
Yeah.
You see, in the case of electric propulsion, is 1/10 is propellant. You see, so the use of the transformation of mass into kinetic energy, the mass of propellant in electric propulsion, and chemical propulsion is more efficient. In that sense, you see, for the settlement, the building of settlement in Mars or a moon, what you need is not a cargo that is delivered with the speed of a rocket, chemical propulsed rocket, but you need a cargo that delivers from LEO to moon in a period not measured than 4 6 months, you see.
Exactly.
Because what you want to have is the total cargo there, and we're talking here about 27 tons. You see, 27 tons in space is more than the current capabilities. Of course, you can put these 27 tons with a chemical rocket, you see, but then you need a much larger rocket, much propellant, and that is exactly the beauty of electric propulsion. You simply help to maximize the overall mission, because the mission is not just, getting to the moon, but this is, the different steps that you have and the different trajectories. And for orbit transfers, is electric propulsion, a more economical alternative. You see, for cargo transfers, also the more economical alternative. And once you put the motion to build these technologies in place, then you will have the development of the infrastructure, of the space infrastructure that you need to, to operate and do economies in the space. So just to go back to your questions, okay, and why the superconductor is a game changer? Well, you need to look at it from the perspective of the different fields of applications of superconductors. Electric propulsion is one of them, you see, but they can be used also in terrestrial applications. For example, airplane electric propulsion. NASA has several roadmaps for airplanes with fully superconductor electric propulsion. So this is not new. In marine, you can use it also for naval submarines. You can use it for cross ships, like Kreuzfahrt. These big cruisers, you see, for tourism. This is big cities, 50 megawatts of power they need. You see, some of these, and they require, very propellants or fuel that is, not good for the atmosphere, etc. So you can go to hydrogen power chips. And this is only on the terrestrial applications, but superconductors can be also applied in other spacecraft applications, like reentry. You see, you have reentry, you can use principles of magnetohydrodynamics, and by using these principles, you can do aerobraking and reduce what is it called, blackout, communication blackout, and also do heat flux mitigation. So basically, what you have is the magnetic field displays the plasma away from the spacecraft by using principles of magnetohydrodynamics and high velocity plasmas. And then you reduce the temperature that the materials have to withstand when they are re-entering. And you know that re-entering is one of the most difficult things you have, especially in Mars. So here this is one of the projects funded by the EU, you can use also superconductors to build toroidal magnet systems that can be applied for cosmic radiation shielding of astronauts in crew missions. There are mission reference, there are already approaches also from European projects on the field. And it is clear that you will never be able to generate such large magnetic fields with conventional technology. So you need superconductors here too. And last but not least, power management and distribution. of a spacecraft.
Mhm.
The larger the spacecraft, the more cabling you will be needing, especially if you need to work with systems of several megawatts, 1-2 megawatts. This cabling can make a very high amount of the total mass, and also because of a very high amount of power heat losses. So with a superconductor power management and distribution system, you won't have this problem, you see. So you will have a most efficient system. So all combined, you have also a storage. You have also, I mean, all the appliances for power distribution, like transformers, fault current limiters, magnetometers. There's a series of appliances that can be used with superconductors and be quite efficient, needed for space. And that is one of the reasons why it is a game changer. I think that is, when you know about it, it makes it quite evident. Sorry if I just talk too much. It's just, you know, when you love.
No, this is really exciting. And I think it's absolutely amazing, you know, Manuel, how these superconductors can, you know, improve power efficiency, mass reduction, the compactness, you know, size reduction of things. So, and I found it really interesting how you said that it actually eliminates the blackout period problem that we currently have when we're, you know, reentering, and it helps with that. So I just found that very fascinating, you know, how something like this can, you know, help solve all these problems. Yeah, I find it quite really fascinating, and you know, I have no doubt that a lot of electrical engineers out there would say the same thing.
Well, I mean, I think electrical engineers are going to, majority of them, they always think it's really cool. You know, superconductors are used here for high voltage DC projects.
So sorry, Manuel, you are going offline again. Can you hear me?
Yeah. Hello.
There we go. There we go. Sorry about that.
Okay. Sorry for the bad internet. So no, what I was saying is that you see, there are already commercial superconductor cables for, you know, for power grids. You see, several kilometers, 220 kilovolts. And this is one of the uses, you know, large transmissions, distribution of power, and in a very dense, very condensed manner. So, and this is gold in space, you see, because you need a space in space, basically. So we hope that in Neutron Star Systems we move forward, you know, on bringing these technologies quite, but at least, you know, we see competition now, we see movements. New Zealand is moving. Australia, I'm really surprised. You know, we try to contact the Australian Space Agency, but I think that they have been like growing, changing, adapting. I mean, they're new, no? I think that they're not really actually, I know certain Australian entrepreneurs. One of them is called from Neumann Space. He's also making plasma thrusters. And I met him in 2016. So yeah, what do you guys have in your portfolio? What do you guys at Melbourne do? Before we go to the last question, I would like to know from you. I read some of the projects you're bringing, but I still didn't quite understand what exactly you do, guys.
Yes. So specifically what I'm involved with. I'm part of the Melbourne Space Program, and we are working on a nano satellite, focusing on deorbiting capabilities, as we want to address the responsible use of space. Now with space junk increasing in space, we want to make sure that we can assist with future nanosatellites being a bit more responsible when they do go into LEO orbit. That if they're non-functional, there's any issues at all, or the mission has completed, that we can actually maneuver the satellite to go into the atmosphere, so it doesn't stay just orbiting and decaying in on orbit. So that's sort of our main. But there's a lot of great organizations that will, like I mentioned before, it is it's a new industry here in Australia, which is quite exciting as it presents a lot of opportunities. So we're going to be seeing a lot of great companies who will be tackling these sort of issues as well. And it's quite an exciting time.
you have also contact with a company doing a rovers for Mars. I read
that we have the what? Sorry.
They're making a rover, a Mars rover.
That's correct. So that's with the Melbourne Space Program. So we have different departments. Yes, I'm not a part of that myself, but definitely be very happy to send you through sort of details and contacts of who you can
put us
regarding
that.
Because
we can assure that they get the payload delivered. With
exactly, which is really important. So.
Yeah, well, I think that if they want to do it cheap and reliable, and one thing that you have with superconductor-based electric propulsion is one of the things is you can increase the power available for the spacecraft, and with that you can increase the computing capability.
Mm-hmm.
You see, you can integrate quantum computing capabilities in the spacecraft and make the spacecraft more autonomous. And for autonomy in space, you need AI, and AI needs fast computing, but also large computing capabilities. You see, and normally you can't do that without quantum computers offer this possibility, but you need power. You see, you need power available for doing all these operations. So you need power anyway. So power is the money, is the coin of for me, is the coin of value in space. How much power you have available, how flexible you can equip your spacecraft. And I think that that's the revolution that potentially superconductors can bring into space.
That is so exciting, and then like I said, there's going to be a bit more of a shift of attention headed towards superconductors and revolutionize that. I believe the University of Texas actually has a whole center as well that is for the sole purpose of investigating temperature superconductors and sort of seeing what can be done and what future inventions it can help with and what problems it can solve. And Manuel, I guess this brings us to one of our last questions here. This is quite important, for anyone who is looking a career into the space industry here. And I suppose, what are the technical things you look for when hiring an entry-level graduate for Neutron Space Systems?
I'm going to be entirely honest with you. More than technical things, what I look is some concrete skills. You see, and for me, the most important thing is that the person is able to address problems by using its own means. You see, I encourage a lot of. We have 8 people, 10. It's not much, but we have several engineers, and for us is kind of like you will be building the PPU of an MPD. So you are an electrical engineer. You tell me, how do you want to do it? Think something through. This is the literature, you see. So it's more like I think that what we're looking for is for people that have a very independent, way of doing things. People that just get hands on the job and do things. You see, get things done. Technically speaking, not physicist. Yeah, physicist. Not physician, physicist. Physicists, mathematicians, not many aerospace engineers with solid knowledge of electric propulsion, if MPD or any other plasma thruster technologies, as a Helicon or any other, is fine. And for us also, what we're looking is also for system architectures. That means system engineering.
Yep.
You see, because we need to think all the different systems for different power classes. So yeah, so that's pretty much what we're looking for. And people that, they don't do this because they see it a mean to get somewhere else, but they do this because they want to have some fun. People that wants to do this, to want to work with us because they just want to finish a traineeship. No, you really want to build this shed if you want to work in Neutron Star Systems, because it's going to be the first one, we hope.
No.
So, well, thank you very much, Celine. I really appreciate it. And I hope that I enlightened you a little bit more in your search for deep tech technologies. Believe me, this is a hard job. This is an absolutely hard job, but sometimes it's a lot of fun, like today, talking to you. Thank you a lot.
Thank you very much, Manuel.